So looking at the Spark deployment mode then, by that I mean, how do we actually use Spark? Firstly, it does come with the ability to run on one machine. Now this is counterintuitive because one machine isn't big data exactly, but it does allow us to have a structure for learning and training and testing things out. So that's local mode. That's the one we'll be using predominantly. It will also run on a standalone cluster, so that means we can collect one or more machines together, link them together using Spark. And in fact, we will see this possibly when we look at the Azure Databricks configuration, where we'll be running possibly running more than one machine. You can add more than one machine to the network. Then there are official cluster modes for things like Mesos and Yarn, which actually handle the construction of complete clusters. So in terms of the workflow, then as you saw before, the Spark application creates the Spark context. We have to have this bound to create our application. So the Spark context registers to the initializes to the driver. That registers to the appropriate cluster manager and asks for resources to allocate executors and schedule execution for the different tasks. Benefits: the applications are completely separate. So the task scheduling is per application. It tries to use threads rather than processes, and threads are a lot faster. Applications can't share data in memory natively, so if you wanted to do that, you would have to use some external product. And it's statically provisioned. Now, one thing it's useful to be aware of is the core data structure, which is the RDD. So RDDs are not the primary way to program Spark as of Spark 2. The preferred way to program Spark is actually using Spark SQL. That does compile behind the scenes into RDDs, but as we'll see later on, Spark SQL allows better optimizations than constructing programs which just use RDDs. Now the thing about RDDs is they're immutable. That means they can't be changed. So an RDD is like an array in that it holds data, but it's not like an array in that you can't change elements. What this means as programmers is rather than changing elements, we take the RDD, we transform it into a new RDD. RDDs either point directly to a data source. It mentions HDFS there. Usually we'll be reading from files, maybe text files, maybe comma separated files or something like that. You can connect to any data source to create RDDs from that. And another key point to note is that Spark uses lazy evaluation. And what that means is it does not evaluate anything until it meets an action. This is quite strange if you're used to working interactively with Python, for example. You run a line, it's executed. If there's an error, it shows straight away. Well, that doesn't happen with Spark. Some actions will cause the preceding computations to execute, and quite a lot which are just transformations will not. So it will seem as though your code has worked till you at some point hit some action which is evaluated, and at that point you'll find that, for example, you made a spelling mistake in a file name. So that's something to be aware of. It does lazy evaluation, and the reason it does the lazy evaluation, as I've said already, is so it can optimize and construct and optimize that directed acyclic graph, which in turn means fewer operations. Fewer operations means that your application would run faster because there's less data being transferred between different executors and therefore over the network and so on. So being aware we will meet lazy evaluation as we go through. You can't avoid that. But understanding why this is going on is also quite useful. So a number of RDD interfaces. So for instance, we've got dependencies on parent RDDs. There's going to be data partitions going on. There'll be some user-defined code. There is something which partitions large amounts of data into different RDDs. This generally happens behind the scenes. However, you can enforce some manual separation if you know something which isn't obvious about the size of the data or the way it's going to be shuffled about. Again, your objective would be to avoid shuffles. The kind of dependencies that we've got, you can see from this graph, some dependencies, such as filter, are 1-1, and they are going to be quite quick. Where we have got, for instance, something like the join, we are going to be transferring multiple blocks around to join two data sets together. And again, this could cause significant slowdown. Wider dependencies, such as grouping data items. So grouping data items, very common operation. And that can, as you can see by the depth of the arrows, this can be quite inefficient. Hello.